Consider two observers in relative motion. In this case, Albert and Henry, just for the sake of argument. At the exact place and time they pass each other, they observe a flash of light. A sphere of light expands outward from that point. Since each measures the speed of light relative to himself, each believes correctly that he is always at the center of that expanding sphere, even though they themselves move farther and farther apart. How can two people in different places both be at the center of the same sphere? To confirm his perception, each sets up light detectors an equal distance apart. However, while Albert's detectors register the light arriving simultaneously, he believes the light strikes Henry's detectors at two different times. Meanwhile, Henry sees the same thing in reverse. They agree on the speed of light, but they disagree on whether events happen simultaneously or at different times. This is not semantics, nor a petty debate. It means that time, as well as distance, has to be affected by motion. Can be seen with the aid of the simplest possible clock. Two mirrors a fixed distance apart, with a light beam bouncing back and forth between them. Each bounce of the beam is a tick or a tock of the timepiece. To Henry, his clock is stationary and altogether ordinary. But for Albert, that clock is moving. And between tick and tock, he sees the light beam trace a diagonal path, which means it's traveling a longer distance. But the speed of light is the same for all observers, so the light must take a longer time to travel the longer distance. Therefore, Albert believes the moving clock runs slow. But how slow?
The relativity of time is derived from the right triangle formed by the distances traveled. The Pythagorean theorem shows that the path of the moving light is longer than the distance between mirrors. By the factor 1 over the square root of 1 minus v squared over c squared. This factor occurs so often in relativity that it is given its own symbol, the Greek letter gamma.
So to an observer at rest, a moving light clock seems to be running too slowly by the factor gamma. A ruler, or anything else in motion, also seems contracted by that same factor.
Okay, so here it is. So here we have at rest, the clock at rest. So this is tick-tack, okay? Tick-tack. So obviously this is c, so velocity of light, and the difference between the tick and the tack at rest, let me call it t0. This is at observer that is moving with the clock. The clock is at rest with respect to the observer. Now assume that we see the same clock, but now it's moving. Now it's moving. So the light leaves from here, but by the time it gets to the top, the clock has moved to here. Right? And then subsequently. So this time, this distance will be, that the clock moves, will be vt. V is the velocity now of the clock with respect to the observer. Are you with me? Vt. So this should be, actually, I don't know, right? This is the same distance. Now, tick was here, but tack is there. So this length is ct. So here we have a rectangle triangle in which this is ct, this is vt, and this is c0. So you know the relation between the sides of a rectangle triangle, right? So what is the relation? The hypotenuse is, the square of the hypotenuse is equal to the sum of the square of the sides. That you know, right? So this is c squared d squared is equal to d squared plus c squared d0 squared. So far so good. So let me put this to the other side. This is c squared minus b squared. C squared is equal to c squared d0 squared. Are you with me so far? Everybody? Let me now divide by c squared both sides. So here I have 1. C squared enters into the parentheses. I have 1, and then minus b squared over c squared. So here I have 1 minus d squared over c squared is equal to d0 squared. So I would like t in terms of t0, which is what I measure when the clock is at rest. Right? So now I pass this dividing is t0 squared over 1 minus b squared over b0 squared. C squared. Thank you. And now if I want t, I have to take the square root of both sides, right? So this is t, this is square root. And as it was said before, this number, 1 over square root of 1 minus b squared over c squared, is given the proper name. It's called the gamma factor. This is the Greek letter gamma. So this is gamma t0, where this is for the time as measured when the clock is at rest, and this is moving. Moving with respect to the observer with a speed c. This is then our result. Now this is almost, well, when v is 0, how much is gamma? Is 1, right? When v is 0, t is equal to t0. And actually this is a function, here you have the function plotted. The Lorentz gamma factor, as it is called, is practically 1 for all velocities velocities which are not very close to the velocity of light. So you have to go to 3/4 the velocity of light before it actually departs from one significantly. Okay? So this is the equation we saw so far. So for example, if V is 85% of the velocity of light, gamma is 2. If V is 0.97%, 99.7%, 0.997, then gamma is 10. For the time being, let me talk about the time dilation. So assume gamma is 2. Now this is time itself. It doesn't, we found the gamma factor using this clock, but any other clock would be the same, because it's time itself, it's not a particular clock. So for example, we have many internal clocks. We read a certain rhythm. This could be peak and attack. Our heart beats. Our cells divide with a particular period. We digest. All our chemical processes happen at particular times. Okay? So if a person on Earth sees a person traveling at, for example, a velocity v, this is one example that I gave, 85%, v is 0.85 of c. This person will see that the heartbeat, okay, takes double the time. All the molecular timings, particular time periods, characteristic time periods, the division of cells, everything, okay, happens twice slower. Okay? The tick and the tack slow down. So the person actually becomes old at a rate which is half as much. So for example, if a person travels, makes a trip of 10 years, goes someplace and comes back, okay? And t with respect to Earth is 10 years. That means that t0, the actual time that elapsed for the person who was all the time at rest with respect to himself is only 5 years. So everybody on Earth would be 10 years older. 10 years had elapsed, but for the person who took the trip, only 5 years had elapsed. If the trip would have been at 99.7% of the velocity of light, 10 years would have elapsed on Earth, but the person taking the trip would be how much older? 1 year. Yes. Because gamma is 2. When V is 0.85 C, this implies that gamma is 2. So as you see here, gamma is 2. So T0 is equal to T over 2 by a particular example. I'm using this equation. Okay? This is very strange. So it assumes that the person took a certain distance. This distance measured from Earth is a distance L0. Now, this is a distance to a star, for example. Says, well, this person went to the star and came back. It took the person 10 years. Now the guy here says, come on, that's not true. I measured all the time, my star and came back. So how come? Certain distance? Something has to give, right? So the guy says, the person in the vessel says, no, only half the time elapsed. But I went there and came back because the distance was half. So this says, imagine that this is a ruler. This is a ruler, L0, which is at rest with respect to the Earth. When this vessel is moving, with respect to this spaceship, okay, this person, of course, is at rest with him or herself. However, this ruler, this distance between the star and the Earth, is moving very fast, right? So, moving rulers, moving distances are seen as shorter in the direction they are moving. So, for example, if I would be moving with respect to you, okay, in this direction, very fast, at 85% the velocity of light, I would say this, which is at rest with respect to me, to be 1 meter, as you are seeing it down. Okay? But you would see it contracted. You would see it as measuring half a meter. If I would be moving like this distance would be still 1 meter for you. This distance, in the direction of motion, would be 1/2. If I would be moving at 99.7 C, okay, I will be moving in this direction very fast, 99.7 the velocity of light. You would see this ruler, how long? How long? 10 centimeters, exactly. So you see that you need both length contraction. This is called time dilation of moving clocks. Time dilation of moving clocks. Okay, by a factor of gamma. And this is the distance, when this distance, okay, the ruler is L0 at rest, but it will be seen only as L. L is equal to L0 over gamma. This is at rest, okay, and this is the moving. A ruler that is moving with velocity v in the direction in which it's moving would be seen as contracted. So let's explain contraction. And both are necessary so that both observers agree. Okay? They have to agree because it has happened. The person was on Earth, went to the star, and came back. Both agree. From Earth, they said, well, you went there, okay, because it took you 10 years. The other person on the vessel says, no, okay, it took me only 5 years, but the distance was half. Okay? Time dilation and then contraction.
The example that we have just seen is called the twin paradox. The story goes that there are two twins and who therefore have the same age. One of them stays on Earth and the other goes to a faraway star, traveling at the velocity close to the velocity of light, the fraction of the velocity of light, so that the effect is measurable, and then comes back, and it is, and this brother who traveled is younger than the brother who stayed on Earth. Now, why this is called a paradox? Well, a paradox is something that at first sight seems not to be true, but in reality, thinking of it again, it is true. So what is paradoxical about this? Well, one can think the following. Motion is relative. So from the point of view of the sibling who traveled in a spaceship, he was always at rest with respect to himself. But he saw Earth moving first away from him and then closer to him or her at a velocity which was a fraction of the velocity of light. From the point of view of an observer on Earth, while the spaceship is traveling, the clocks in the spaceship are slowed down. But from the point of view of the spaceship, the same thing happens while the ship is moving at constant velocity. The person is at rest with respect to himself on the ship, and he or she sees the clocks on Earth moving slower than they should. So at the end of the day, which of the two brothers is younger? And the resolution of this apparent paradox is that only one of them was accelerated. Accelerated observers are non-inertial observers. And an observer can distinguish if he or she is accelerated or not. So the person in the spaceship can measure that it was him or her, the person traveling, that was initially accelerated to get to a velocity, a fraction of the velocity of light. Then when it got to the start, it had to be accelerated back again to return. And then it had to be slowed down, another acceleration. So there are 3 periods of acceleration. In these 3 periods of acceleration, the sibling who is traveling has to change from one inertial frame to another. And at that point, it has to adjust its measurements of the clocks on Earth. So in reality, the younger brother is the one, the younger sibling is the one that traveled, that was accelerated. Now, if you were even more inquisitive, you could say, well, but you know, the brother that stayed on Earth was accelerated too, in this case by gravitational forces, because it's going around the sun. Together with the Earth is a rotation, and therefore the velocity is not constant. Well, in order to answer to this question, one has to go to general relativity, which is a theory of gravity. It is still correct that the brother who stayed on Earth, who moved on what's called a geodesic, as we are going to explain in our class on general relativity, would be older than the brother who did not stay in a geodesic path, who was accelerated. So it's always the accelerated sibling who is younger. So we don't have these siblings, one of whom travels and so on. This is very unlikely to happen anytime soon. So where are relativistic effects important now, here and now? They're important every time we have, for example, particles that are moving at close to the velocity of light. And this happens in cosmic ray showers. Cosmic rays are particles which are moving already at relativistic speeds and incoming on Earth, interact on the air, with the air in the atmosphere, and they produce showers of particles. And for many of these particles to reach, as they do, to reach the surface of the Earth, time dilation and length contraction are essential. They wouldn't reach Earth otherwise. Of course, these effects are very important in particles accelerated in accelerators. We accelerate particles, physicists accelerate particles to study them. This is, for example, at this point, the Large Hadron Collider, the largest accelerator at present. It's at CERN, a laboratory called CERN, in the outskirts of Geneva. And you can see the relative size on the bottom right corner of the picture. You can see the size of the International Airport of Geneva with respect to this big ring that is the Large Hadron Collider. So we observe relativistic effects every day in colliders. There is another application that actually affects you directly. I bet that many of you have a GPS system in your car, for example. And relativistic effects are very important for the global positioning system. This is a system of satellites that are moving around Earth, and they emit signals saying where they are and what is their time, the time that they measure with atomic clocks that are in the respective satellites. Now, these satellites are moving with respect to any observer on Earth. These are moving clocks. Therefore, time dilation has to be taken into account. What is the precision needed to get a measurement, to get the precision in distance of 1 meter, which is about what your GPS systems can give you? Well, the signals that reach us from the satellites move at the velocity of light. So they go over a distance which is 1 meter in about 3 nanoseconds. So distance over the velocity of light gives you the time. So the precision in time needed in order to give your position within 3 feet, which is 1 meter, is a few nanoseconds in time. 1 nanosecond is 1 over 1,000 million of a second. Now, if time dilation would not be taken into account, because the satellites move at 14,000 kilometers per hour, which is not a relativistic velocity by no means, the GPS time would be off by 7 microseconds per day. 7 microseconds per day doesn't seem to be much, but 1 microsecond is 1 millionth of a second. And the precision we need is much better. So an error of 7 microseconds in time would give you an error of several kilometers in position, which would completely invalidate the GPS system, would make it completely useless. So time dilation needs to be included. And also there are other corrections that are even a bit more important, which are due to general relativistic effects. The last subject we are going to cover in the class is a little bit of relativistic dynamics. So as you have seen in classical mechanics, the momentum is just the mass of a particle multiplied by its velocity. But the relativistic momentum has a gamma factor, where this is the Lorentz gamma factor that we talked about earlier. This gamma factor is 1 over 1 minus v squared over c squared square root. And remember what we mentioned earlier. The gamma factor is practically equal to 1 until we get to velocities that are closer to 3/4 the velocity of light. The relativistic energy is also proportional to gamma. Is in this case gamma mc squared, where c is the velocity of light. Now, we can use the following approximation for velocities which are much smaller than the velocity of light, namely if v over c is a small number. So you can take, for example, v squared over c squared 0.1 or 0.01, a small number, and then you can check just with a simple calculator that for small values of the ratio v over c, this 1 over square root is the same as 1 plus v squared over 2c squared. So for velocities which are much smaller than the velocity of light, namely the velocities we encounter every day, I can replace gamma by 1 plus v squared over 2c squared and see what I get. So this is 1 plus v squared over 2c squared mc squared. So when I open up this parenthesis, I get mc squared, and then I multiply mc squared with the second term. C squared with c squared go away, and I have m over 2 v squared. So you would recognize this as the kinetic energy that you have been using. And you see that when the velocity is 0, there is this energy remaining, which depends directly on the mass of the square, so on the mass of the particle. So E equal to mc squared is called the rest energy of a particle. So we can see, first of all, that the energy and momentum of a particle, relativistic energy and momentum of a particle, are proportional to gamma. So this means that no massive body can be accelerated to reach the velocity of light. And this is because when v is equal to c, the gamma factor becomes infinite. Namely, we would need to give a body, a massive body, infinite energy, which is impossible to give, for it to reach the velocity of light. Therefore, no massive body can ever move at the velocity of light. You can get close to it in principle, but you cannot get to the velocity of light. Now, this is an equation, E equal mc squared, a very famous equation, and for good reason. So here you will recognize these mushrooms. So these are photos of the atomic bombs which exploded in Hiroshima and Nagasaki at the end of Second World War. And here you have a picture of stars. So what atomic bombs and stars have in common? Well, they are both fueled by the effect of this equation. There are nuclear reactions in which mass can be converted into energy. Namely, nuclear reactions in which the final mass is smaller than the initial mass, and the difference in mass multiplied by c squared is released as energy. This can happen through nuclear fission, in which a large nucleus divides into other smaller nucleus, or nuclear fusion, in which smaller nuclei form a larger nucleus. But in both cases, the final mass of all the reaction products is smaller than the initial mass. And by not much. For example, for fission, here you have at the beginning you can have 236 units of mass, which is a proton mass, and at the end you have 235.80. I mean 0.2 of a proton mass. This is a small mass difference, but of course there are many, many nuclei that are in a particular reaction. Now, fission is what is at play in atomic bombs, in the energy released by atomic bombs, A bombs, and in all functioning at present nuclear power plants or nuclear reactors use fission. Fusion is at the basis of the energy released by all the stars, including our sun. So we owe our life on Earth to nuclear fusion. It is also what is used in H bombs or hydrogen bombs. And it is what is used in controlled fusion or hydrogen reactors. At this point, hydrogen reactors consume more energy than they produce. But if this balance could be reversed, I mean, if they could be made to produce more energy than they consume, then they would provide clean nuclear energy. And many people are working in this idea, in this possibility. So you see that the importance that it has for our everyday life, special relativity.